Unit 3. Unit 3 is titled Energy. And energy is going to be about the most fundamental definition and the most fundamental topic that we talk about throughout this entire semester. And what I mean by that is everything else kind of centers around energy. If we know how much energy is either going into or out of a chemical reaction or a physical change, we can very easily describe that chemical reaction or physical change. 3.1, the first section in Unit 3, is called transferring energy. So we want to understand how energy gets transferred from one system to another. So take a look at our model to this point. We've defined temperature, and we've done so by saying that it's essentially a measure of the degree of hotness of a sample. What I would say about that is if we take all of the kinetic energies of every single water molecule in a beaker, and we take the average of those kinetic energies, that's essentially the temperature of that sample. We can also call that the degree of hotness. We're pretty well aware that when the temperature increases, the speed of the molecules increases, and this then causes our substance to expand. And it's this expansion that allows us to find temperature in thermometers, just like we've done with previous demos and like we've talked about in previous notes. But let's take a closer look at temperature, and by investigating temperature, we're going to come up with a term that we've talked about in Chapter 2 again, heat. And heat is going to allow us to talk about our new term in this chapter, which is energy. So I've got the following analogy. I've got a large bucket over here, and it's full of water at 50 degrees Celsius. And then I've got a small teacup on the right side, which is also full of water at 100 degrees Celsius. I might ask the question, or might say the statement, the molecules obviously move faster in the cup. We said that as the temperature goes up, the molecules speed up. We then can say that the teacup has a higher degree of hotness, and thus it's got a higher temperature. But I might ask you this question: which is more effective in warming a swimming pool? Would you pour the teacup in the swimming pool, or would you pour the large bucket in the swimming pool? Hopefully you can conclude that the bucket is the one that we would use to pour into the swimming pool. Now, why is that? Well, instead of molecules, let's fill each of our buckets now with money, which is kind of fun. So the bucket's full of, let's say the bucket's full of $50 bills. And let's say that the teacup is full of $100 bills. I might ask the question, which would you rather have? The $100 bills are certainly very tempting, but there's certainly not nearly as many of them in the teacup as there are $50 bills in the bucket. So the bucket, being so much bigger, contains so many more bills than the teacup does. You'd be foolish to take the teacup. You'd go ahead and take the bucket. So this analogy is what we kind of can use to explain why the bucket would be the better choice when filling up your swimming pool. Now again, degree of hotness is, in this case, it's the value of the bill, so it's the 100 or the 50. The degree of hotness is higher in the cup, and thus the cup is a higher temperature. But the quantity of hotness is higher in the bucket. The quantity of hotness is higher in the bucket. And that, my friends, is heat. That is heat. Now, heat is not a substance, but is an entity that can flow. Heat flows. So heat can flow from the bucket into the swimming pool, thus warming up the swimming pool. But it's interesting to ask the question, well, where does that heat come from? So heat has to come from energy. And energy can be stored and it can be transferred. And it's going to be our job now in these next two slides to look at how energy is stored and how it's transferred. We can take a look at like a money analogy for energy. So energy is stored just like money, and it's essentially stored in one of three accounts. So if we can use a money analogy here, let's look at three different accounts. And we'll call this one our checking account. And we'll call this one our savings account. And we'll call this one our debit account. So this is where the money is going to. Okay? So we can continually transfer money between accounts. We can take our checking account dollars and we can transfer checking account dollars to the savings account. We can take savings account dollars and say, "Ooh, I need a little bit more back into the checking," and I can reverse that. I can go here. I could possibly have to pay somebody out of my checking account, so I could swing that there. Maybe I get paid on payday, so I can take my debit account and I can shift that back into my savings. The main thing here that I want to prove is that the money is always ending up inside of an account. And this is energy. This is the same idea. Energy is always there. It's always present. It doesn't ever get destroyed, and money never gets destroyed. I mean, yeah, we could burn money, but that'd be bad. We don't want to do that. Money itself just never gets destroyed. It never. If you think about yourself going bankrupt or becoming broke, it's not that that money disappeared. It just went to somebody else. Somebody else has benefited off of your misfortune. And energy is the same type of thing. If you run out of energy, it's not that it has disappeared, it's just gone somewhere. If you run out of gas in your car, and you are now pushing your car to the gas station, it's not as though that energy that you had previously used has disappeared, it's just gone to other places. So the three different accounts, as far as energy is concerned, are not checking, savings, or your debted accounts. The three different accounts start with thermal energy, which we'll abbreviate E with a TH in subscripts. And this thermal energy is the energy stored by moving molecules. So some of the energy that we know of as it comes to chemistry, as it comes to chemicals, is stored in the movement of molecules. So an example here would be hot water as compared to cold water. The hot water molecules moving faster inside of the teacup have more thermal energy as compared to cold water molecules in your water bottle inside of the refrigerator. The second account that energy can live in is called the phase energy. Phase energy is the energy due to the arrangement of molecules. It seems a bit funny as though there'd be energy just due to the arrangement, how molecules are positioned. But you have to understand this, that identical molecules, like water molecules for instance, attract each other, or they bind. So when water molecules are in the liquid state, they actually attract one another. This is why they form nice little droplets. And we obviously know that if they get cold enough, they really attract each other and they form ice. But even in the gaseous state, water molecules attract each other, so they bind. The tighter the binding equals the lower the energy. So if we really have tightly bound molecules, like we would maybe in the solid state, we have lower energy. If we have looser bound molecules, like we do in the liquid state, we have higher energy. Now I know this is a bit weird with water, right? Right at that between 0 and 4 degrees Celsius, where ice actually becomes less dense than water. Well, let's forget about that for right now, because for the most part, solids are always more tightly bound than their liquid cousins. The third account that energy can be stored in is called chemical energy. And this is actually due to the attractions of the atoms inside of the molecules. Make a big distinction here between phase and chemical. Phase energy is between molecules. So if I draw a water molecule, and I draw a sister water molecule, the phase energy that I'm referring to is the energy that is between those two molecules, allowing them to attract one another. On the other hand, the chemical energy that I'm referring to is the energy that is stored inside of the bonds. There, and there. That is the chemical energy. When atoms break free from one another, energy can be given off. And a great example would just be exploding gasoline. When gasoline explodes, you're taking the octane molecule, which is 8 carbon atoms, and you're essentially busting everything apart, carbon and hydrogen. And when you do that, you get an incredible release of energy. Now, one thing I haven't talked about here is that we can do the opposite as well. We can actually, when we break atoms, we can actually absorb energy from the surroundings. Okay? So those are 3 different accounts for energy. Now lastly, transferring energy. I said energy can be stored and it can also be transferred. Energy is never, at any single point, it is never created or destroyed. But it can be transferred. And this is known as a very, very specific law. It's called the Law of Conservation of Energy. That's what LOCE stands for. You're going to see me abbreviate it from here on out. Law of Conservation of Energy. Energy can be transferred in 3 ways. It can be transferred via heating. And heating just means that energy flows from one substance to another. A great example would be like a pot if you're doing macaroni and cheese on a gas stove. And that's very obvious, that's very visual, we see that. So energy can be transferred via heating. It can be transferred via working. And this is a bit different. What do I mean by working? This is the energy transfer due to forces between objects. Rubbing your hands together. Go ahead and do it. If you do it long enough and you do it fast enough, you're going to notice that some heat is actually generated. That's energy being transferred from hand to hand. And then lastly, radiating. Radiating just means that energy being transferred by photons, or light. And this is just exhibited by the sun giving off energy to the earth. So now we know that energy is stored in 3 different facets. It can either be stored in thermal energy, or phase energy, or chemical energy. And if we want to transfer that energy between any one of those storage areas, we can do so either by heating it, working, or by radiating. That's 3.1.